Hello again, this is Galen Pickett, Cal State University Long Beach, Physics 151. Today I want to talk to you about 7.3, Path Independence of Potential Energy. And the example I have here for you is, well, the authors of the book like Tarzan, I like Spiderman. So here's the situation. Here is an anchor, some building, something that is in New York City. Spider-Man is going to anchor a web there, swing down to street level, where there is a villain about to create some havoc. Spider-Man is going to grab the villain, and then they're both going to swing to a target building that is height little h on the other side of the swing. And I want to know, is Spider-Man going to make it? He's an expert with this web, he knows the city, he knows whether he's going to make this or not, but we're going to calculate whether he can make it. So, the director says, there's three separate things that happen in this problem. We'll use the energy principle on the way down to find out what is the collision velocity between Spider-Man and this villain. There's going to be an inelastic collision between these two things. So we use the momentum principle to analyze the inelastic collision. And then we'll use the energy principle to figure out how that combined object swings. This combined object would then have a mass of 2m, so Spider-Man and the villain have the same mass for this problem. And then use the energy principle for the way back up. What do we know from the problem? We know capital H. We know the masses involved. Let's say we know the value of little g. What do we not know? The unknowns. We don't know the v of Spider-Man at the bottom of the swing. We don't know the velocity after the collision, and we don't know little h, and little h is the thing we're looking for. So, investigator. First, let's use the energy principle. So, this is a section about the path independence of the potential energy. I know that Spider-Man is going to be doing this half-circle path, but that's not relevant for figuring out how the potential energy for the gravity interaction is going to work out. That's one of the reasons the potential energy is so important. So, we'll put Spider-Man, the villain, and the Earth into the system. So I've got a kinetic energy, and an interaction energy. So, now we've got a closed system. The surroundings are nothing. So, the energy principle is going to say, for this process going from state number 1 here to state 2, delta E system is equal to the work from the surroundings, which is 0. So my initial energy, Spider-Man's kinetic energy, is 0, the villain's kinetic energy is 0, and the gravitational potential energy is Spider-Man's mass, g capital H. At the bottom, I have 1/2 m v bottom squared. That's Spider-Man's kinetic energy, plus the villain's kinetic energy, plus the gravitational potential energy. So that is equation number 1. And now we do the collision momentum principle. We'll say that the system is the same one, Spider-Man, the villain, and the Earth. So that collision happens. My initial state is Spider-Man's mass going with the bottom, and here is the villain at rest. That's the initial state. The final state is the two of them together just before they start to leave the ground. They've got what I'm calling the final. So, again, the most important forces in the system is going to be tension on the web upwards. There is no component of the force in the x direction. So, if I look at the momentum of the system in the x direction, its change is equal to F net in the x direction times delta t, which is equal to 0. So, I get the initial system momentum, m times v bottom, plus the villain's initial momentum is equal to mass times v final plus mass times v final. Spider-Man and the villain are both going together, and that is equation number 2, and that should look a lot like the inelastic collision between the ball and the spring ratchet deal. And now the energy principle on the way back up. And here, just to make the point that I can change the system, I'm going to change the system to be Spider-Man and the villain. And now Earth is in the surroundings. So now the energy principle, it's not an isolated system. We've got, here's the initial state. I've got these two objects going with the final. And then I've got these two objects that are at rest. And they've gone a distance little h upwards. So now the work from the surroundings is equal to the displacement here is going to have some delta x. The y displacement is going to be h. It moves h upwards, and the z displacement is 0. And I dot that with the force from the surroundings, which is 0 minus mg 0, and I get minus mg little h. Oops. It's not mg here. It is minus 2mg, because I've got the two objects gives the force there, so minus 2mg, that is the work from the surroundings. The change in the energy is now, my initial energy is 1/2 times 2m v final squared, and then I subtract the final kinetic energy, which is 0, and that is equal to, oops, that's backwards, because I've got the way these are labeled. This v final is the final after the momentum principle, but it is the initial for this state, and there is the final. So the change in energy, the final is 0, the initial is 1/2 times 2m times v final squared, and that is equal to minus 2mg little h, and that is equation number 3. So we solve equations 1, 2, and 3. Execute. I've got 3 equations and 3 unknowns. So equation 1 tells me correctly that, notice that Spider-Man's mass is going to cancel for that one, so I get v bottom squared is equal to 2gh, and that's it. So v bottom equals square root 2gh. Let's put that into equation number 2. So I get m times square root 2gh is equal to 2m times v final. The m's cancel off, and I get that v final equals square root of gh divided by 2. I just took the divided by 2 there, and then wrote it as 1 over the square root of 4, and then canceled. And now that we're going to put into equation number 3. So notice that there's negative signs on both sides there, so I get m times v final squared is equal to 2mgh. Cancel the m's off. V final squared is gh divided by 2, which is 2 times g times little h. The g's cancel off, so I get little h is equal to capital H divided by 4 is the answer. And now we do the skeptic review. There are no unknowns, and the units are fine. Those are the first 2 checks you always do. But h divided by 4 is interesting. I do have 2 objects that are being raised a height little h. So if I think of mgh as the initial energy budget for the system, if I take that same mass, I double it, so I have 2m times g times little h, you could think to yourself that little h should be capital H divided by 2, because I've got 2 masses that I'm lifting up. But this initial energy budget of the system, 1/2 of it goes into the internal energy of the collision. This is an inelastic collision. 1/2 stays as kinetic energy, and then that kinetic energy will go to mgh, gravitational potential. So I start with mg capital H is the total energy. I multiply by 1/2. That is the factor that's still in the kinetic energy, and that is equal to 2mg little h. And that's how we get h divided by 4, which is the right answer.